Okay, great. Good morning, everyone. My name is Justus Posthuma, and I'm affiliated with the School of Data Science and Computational Thinking from Stellenbosch University in South Africa. I'll be sharing with you today some interesting results obtained in our study of using a contract-driven test-interceptor-based software development approach. So in software development, one of our main goals is to produce quality code. As a developer with more than 20 years experience, I've seen and written my share of bad quality code. And as I've gotten older and wiser, I've come to realize the importance of good quality code. Fortunately, IT companies around the world also realize this. They are spending upwards of 40% of their budgets on quality assurance and testing. So what is good quality software? We define good quality software as components where one is able to verify that the component meets the specified requirements, and the code is good code in the sense that it meets the required coding standards, including being free from typical coding errors. Additionally, one should be able to validate that all stakeholders who have requirements have been identified, and the requirements themselves are correct. In other words, complete, consistent, and minimal. How do we assure that software components are good quality? It comes down to testing, testing, testing. These tests can either be performed manually or they can be automated. Manual testing has a number of disadvantages. It requires more time and resources, so a developer or tester has to create test cases from the requirements and run them manually every time the code changes. It is less accurate since humans are prone to make mistakes. Performance testing cannot be done manually. It is not practical to organize hundreds of machines and testers to determine if a software component is able to handle load. Software change requests take more time since every test case needs to be run by a tester to ensure no errors were introduced by the update. Manual testing is a tedious process since all tests have to be run every time an update is made to the code. However, when it comes to tasks like testing the user interface of an application, only manual testing by a human can determine the usability of the application. Automated testing, on the other hand, addresses all the disadvantages of manual testing. Much less time and resources are required. The tests are written once and can then be executed as many times as is needed. Tests are much more accurate because once the logic is correct, the testing tool will execute the exact same logic every time the test is run. It is possible to do performance testing since multiple instances of the testing tool can be executed, for example, by using threads or virtual machines. Software change requests can be done much faster since running the automated tests will quickly show if an error was introduced by the update without having to wait for a tester or quality assurance person. Automated testing is not tedious since the tests are run automatically by a testing tool and seldom require any human interaction. Additionally, automated testing has the following advantages. Automated testing is normally part of the build process of the application. Every time changes are made and the application is built, the tests are executed and the developer will immediately see if his updates to the code have introduced an error. Test scripts can be run unattended, freeing up resources. Over time, automated testing is cheaper than manual testing since it requires little to no resources or time. But irrespective of the type of testing performed, testing can only be meaningful if we have testable requirements. In order to make requirements testable, they need to be formalized and quantified. The formalization of requirements involves expressing the requirements using a formal requirement specification language, whose vocabulary, syntax, and semantics are based on mathematics. This allows statements to be evaluated by software tools to prove that the program conforms to its specifications. The quantification of requirements involves categorizing the requirements and defining common attributes for similar requirements. These attributes need to be measurable and unambiguous. So armed with testable requirements, we are able to perform functional testing to ensure that the application is doing everything it is supposed to do correctly. Non-functional aspects like performance, usability, and robustness are also important, but for the purposes of this study, we focus on functional testing. Functional testing uses either black box testing, in which the tests are purely derived from the requirements, or white box testing, in which someone with knowledge of the implementation is able to create more comprehensive and detailed tests. Types of functional tests include unit testing, which is where individual parts of the system are tested in isolation, ensuring that inputs result in the desired outputs. Integration testing is used to ensure that individual modules of code work together properly as a group. This is often done in concert with unit testing. Regression testing is used when developers update code to ensure that the component still functions as expected and that the updates did not introduce any errors. System testing, which is also referred to as end-to-end testing, is where the whole system is tested in its entirety. There are a number of modern software development methodologies that are used by companies in their efforts to produce quality software. The two most popular methodologies today are test-driven development, or TDD, which requires software components to be converted into test cases before development starts. The developed software is then tested repeatedly against these test cases as it is being developed. TDD is primarily used to test units of code, in other words, unit testing, and aims to ensure a set of operations is performed correctly. Another popular methodology is behavior-driven development, or BDD, which is similar to TDD in that it requires tests to be written first. But in the case of BDD, the test describes software behavior by using a domain-specific language. The domain-specific language uses natural language constructs that describe the required behavior and expected outcomes, and is converted into executable tests by specialized software. BDD is also sometimes referred to as story test-driven development, acceptance test-driven development, or example-driven development. The main disadvantage of TDD and BDD is that it requires a great amount of extra effort from developers to write tests. In the case of BDD, developers additionally have to learn and use the domain-specific language and specialized software. This results in extra time and costs on a project. Another major disadvantage is that the tests need to be updated and maintained when the code is updated. This made us wonder, is there a better methodology? So let's talk about contract-driven development. Contract-driven development, or CDD, is a development methodology that aims to produce correct software through formalized requirements in the form of component contracts, which include specification of preconditions, postconditions, and invariants. The methodology has never really gained significant traction in industry, mainly because of the perception that the added effort and complexity of formalizing component requirements in component contracts is tedious and does not deliver enough bang for your buck. But would contract-driven development contribute significantly in the quest for correct, bug-free software if the complexity and tediousness of implementing contracts can be mitigated? Would the level of quality of the software produced by using a contract-driven development methodology be worth the effort of utilizing contracts? In this study, we investigate whether the benefits of generating test logic from component contracts justify the cost of requirements formalization while preserving the benefit of improving the quality of the produced software. We consider an approach where the process of formalizing requirements is simplified by encoding contracts within the programming language itself. Finally, we automatically generate test interceptors to validate contracts, which are used for unit testing, integration testing, and operational testing. We obtained empirical data from an actual software development Java software development project by using a contract-driven development methodology to specify component contracts. Using this data, we empirically assess the following items: the development productivity, which is the rate and cost at which software is produced; development reliability, which is the ability of the process to reliably produce software at a given rate and quality; process usability, which is the ease with which contract-driven development can be introduced; and finally, process scalability, which is the ability of introducing contract-driven development to large development teams. We represent component contracts in Java as Java interfaces, which are annotated with the component's functional requirements. In other words, the pre- and post conditions, and in the case of stateful components, invariance constraints specifying enforced symmetries. A class implementing the Java interface is required to meet the component contracts and will be tested against the functional test logic generated from the component contract. From component contracts, we generate test interceptors, which are interface compatible with the component and which, in the context of service provision, verify that the wrapped component fulfills the functional requirements specified in the component contract. So how exactly does this work? We have created a library that processes the annotations and automatically generates interceptor classes. When a method or service is called on a class, the interceptor does the following things. Firstly, it checks if all the preconditions are met before the service is provided, and if all the post conditions are met after the service has been provided. If any pre or post conditions does not hold, the relevant exception is thrown. It also checks for invariant constraints. This means that it checks the state of the system before the service is provided and again after the service has been provided. So the system must be in a certain state before the service is provided, and after the service has been provided, it must be in the same state. This slide shows a simple example of an interface in which contracts for the component have been encoded using annotations. The generate interceptors annotation tells our tool that an interceptor should be generated from this interface. The invariant annotation means at the beginning and at the end of each method call, this contract should be true. So in this example, there should be no open DB connections before the method is called, and the same should be true after the method is finished. In this way, we can check that the method closes any DB connections it might have opened. Precondition defines a contract that will be checked first, right after the invariant check. That must be true before the component will continue doing anything else. If it is not true, the specified exception will be thrown. There can also be multiple preconditions. Postcondition defines a contract that will be checked at the end of the method execution. There can also be multiple postconditions. And as a final step, the invariance check will be performed again. This slide shows how you would use the interface in a Java class. There is nothing new or weird here. This is exactly how a developer would normally implement an interface with or without interceptors. This just shows that using interceptors is not intrusive and it does not need any complex additional code. From a developer perspective, life goes on exactly as normal. This slide shows the start of the automatically generated interceptor. Like the normal Java class, this is also just a class that implements the interface containing the contracts. The difference here is that this interceptor class acts as a wrapper. So here in the constructor, we pass the normal class that was created in the previous slide. This original class is then saved in the counterpart variable, and each time a method is called on this interceptor class, it will call the same method on the original class, as we'll see in the next slides. This slide shows the rest of the interceptor class. As you can see, it has the exact same method as the original class, but here we also validate the contracts that were defined in the annotation of the interface. And remember, this class and methods is automatically generated. The first thing we do is to evaluate the preconditions. There will be a test like this for each precondition defined. Then we test the invariance by calling validate consistency to ensure the component is in a certain state. If any of the preconditions are false, we throw the associated exception before doing anything else. There will also be a test like this for every precondition defined. If all the preconditions hold, we call the actual method on the original class. After that method finished, we check all the post conditions defined. If any of them do not hold, we throw an exception. Finally, we check the invariant or the state of the component by calling validate consistency again. This will also throw the relevant exception should the component not be in the correct state. This slide shows the only out of the ordinary change a developer has to be aware of to use the interceptor mechanism. Firstly, you have to enable interceptor generation by setting validate contracts to true. This is a main switch that enables or disables interceptors over the whole system. And then instead of the normal way of instantiating a class by using new, you would instantiate a factory and use the factory to create the class for you. If the validate contract system property was not set or it was set to false, this factory would return a normal class as if you'd created it by using new. But in the case where validate contracts is set to true, it would return you an interceptor that wraps a normal class, and it will validate the contracts every time a method on the class is called. And that's it. Everything else happens automatically in the background. This slide just shows an actual example of an exception that occurred during integration testing where a precondition was not correct. I just want to highlight a few things. The annotation processor library is invoked as a pre-compilation step. This means that interceptor classes are automatically generated each time the project is built. This does not significantly impact the build in terms of time taken and resources used. We got it optimized so that each interceptor generated takes literally milliseconds. So where are the test interceptors used? They are used in unit testing, integration testing, and operational testing. In the case of unit testing, the component is meant to be tested in isolation, assuming that any component it depends on performs their task correctly. To this end, one substitutes any dependencies of the component under test with mock objects for these dependencies, which behave as would be expected from the components they are mocking. Dependency injection can be used to inject mock objects instead of actual components for the component dependencies. In the case of integration testing, the component is tested within its actual environment. In this case, one injects real components for component dependencies. For operational testing or testing on the live system, one can dependency inject test interceptor wrapped components for those aspects of the system you want to monitor for contract compliance. Now we come to the project where all of this was put to the test. In January of 2021, work started on a COVID-19 vaccination project at one of our clients. The goal of the project was the creation of software components with these features. It must present a short survey to users to enable managers to gauge the interest in vaccines. It must enable students and staff to make appointments to receive the vaccine. It must cater for signing digital waivers. It must generate push notifications with reminders for vaccine appointments and other important information. And users must be able to report symptoms and side effects of the vaccines. For this project, we used a contract-driven development approach whereby requirements were converted into component contracts. The contracts were then embedded in components using Java annotations. The impact of the approach was determined by comparing our approach to a previous project of similar scope, activities or screens, and REST API calls. The other project followed the normal company standard agile methodology without contracts and interceptors. To quantify the impact, we looked at the following measures for both projects by analyzing data we obtained from the project management software and bug tracking software used by the company. Firstly, we looked at the number of man-hours to develop. This includes requirements specification, requirements refinement and design, testing, and bug fixing. Then we looked at the correctness of the produced software. This is the rate at which the produced software meets the client requirements. It entails producing correct results and handling exceptions properly, and can be measured by counting defects over a period of time with bug tracking software. Finally, we looked at the bug density. This is measured by dividing the size of the module by the number of confirmed defects. The number of hours were very similar between the project with contracts and interceptors versus the project without contracts and interceptors. The result shows that the introduction of contracts does not significantly impact the duration of the project. The average bugs per day was less in our project with contracts and interceptors versus the project without contracts and interceptors. We did not include cosmetic bugs in this measurement. There was a significant improvement in the bug density of the projects that utilized contracts and interceptors compared to the project without them. This was especially true for integration and logic bugs. Cosmetic bugs are high in both projects due to the fact that the client is notorious for always requesting layout, label, and graphical changes, which they log as bugs. Our current implementation does have a couple of limitations, however. Contracts are Boolean expressions, and these expressions are defined as strings. So the compiler cannot do any syntax checking on the expressions. You will only see an error in the expression after the interceptor is generated, and then you will have to correct the error in the annotation and rebuild the project. Another limitation is that interceptors cannot yet check for exceptions as part of a contract. For example, if you want to check for a date format. In Java, the simplest way to do that is to use the simple date format class. If the date format is not correct, it throws an exception. But there are ways to get around that. For example, to create a specific utility class that will test the date format, catch an exception, and then return false. It's a bit more effort, but it is possible. The conclusions that we've reached from this study are as follows. We have found the Java programming language to be very suitable for contract-driven development. Language features like annotations and reflection were extensively used to define contracts and generate interceptors. The fact that interceptors are generated as a pre-compilation step also makes the process easy and seamless from the perspective of a developer. Developers were able to easily implement contracts since the learning curve was not steep at all. Everyone was familiar with annotations already since it is an existing Java language feature. And everything else like interceptor generation and evaluation of contracts happens automatically. It was easy to convince the team to try our implementation of contract-driven development since it had so little impact on the normal development routine. Our empirical measurements show that providing a tool suite for contract-driven development, enabling developers to specify component contracts and automatically generate test interceptors, significantly improve the quality of the software produced by the software development process without increasing the cost significantly. In particular, logic and integration errors were reduced by approximately 50%, and the increase in number of man-hours was less than 5%. We think that even more efficiency benefits can be obtained by automating the generation of test data for unit testing. Based on the results obtained so far in this study, we are confident that we are on the right track to rekindle a renewed interest in contract-driven development in industry. And we feel that this study also demonstrates that the developer-centric approach and tool suite for contract-driven development does deliver enough bang for your buck. For future work, we will be looking at automating the generation of test data from the contracts for unit testing. In particular, generating unit test templates, which require only the population of data structures with test data. We also feel that these results warrant a contract-driven development approach in other programming languages, especially JavaScript, which is very popular on the server side. One would have to scrutinize the specific language features to decide how best to implement contracts, because not all languages have built-in annotations. But in the case of JavaScript, our early investigations show that comment blocks can be used to define preconditions and postconditions for methods. And interceptors can be generated by launching an external process that parses the comment blocks and generate interceptors. Thank you very much for your time.